Hi, everyone. So we have just wrapped up U substitution, which is a technique you can use to integrate things that look like you shouldn't be able to integrate them. And so now what we need to talk about are a couple of ways that we could simplify expressions to make them so that we can take an antiderivative of them. And these are really just throwbacks to things that you learned in Algebra 2. These are pretty obscure methods that don't pop up a crazy lot, but you do want to be familiar with them. And again, it's more of just reminding you of techniques that you already know from previous courses. So this video is going to focus on the use of long division. Hopefully you remember polynomial long division. I'm also going to recap synthetic division, which works sometimes, not always. And then the next set of examples I'll do a second video for. So for this first one, right now, this does not look like something that I could integrate easily. I don't recognize that as the derivative of something else. It's also not really a U substitution situation because I'm not seeing that kind of typical function inside a function thing. I don't have anything inside of something else. So this is what I'm trying to integrate. So what I'm going to do with this is I'm going to take this piece off. I'm going to just kind of step down here for a second. And I'm going to use polynomial long division to simplify this expression. So I'm going to say x plus 1 divided into x squared plus 3x plus 4. Should probably point out that another possibility would be to factor that top expression, because if you could factor that top expression and have one of the factors be an x plus 1, then you could just cross those things out really easily, and you would save yourself all of this. You could avoid having to do division. I will tell you that the first time I did this problem, that's what I tried to do, but that top does not factor as easily as it looks like it should. So we are going to be stuck with division here, and you'll see why in a second. But so again, just reminding you how this works. We're going to ask ourselves, x times what makes x squared? Well, that's an x. And then I'm distributing this x over here. So x times x is x squared. And x times 1 is 1x. Trickiest part of the division process is remembering that we're subtracting right here. So the x squareds are going to cancel out. They should cancel out. We designed it that way. And then here I'm doing 3x minus 1x. So this is going to be 2x. And then bring down the plus 4. Okay. And now the question is, x times what makes 2x? Well, that would be a 2. Let's distribute. So 2 times x is 2x. 2 times 1 is 2. Again, remember that we're subtracting here. And this cancels, and 4 minus 2 is 2. So that's our remainder. Just a reminder on what to do with the remainder. The remainder becomes a fraction on top of this x plus 1. So this is now going to be a 2 over x plus 1. Okay, so now if I go back to my original problem, I can rewrite this, and I can say, actually, what I'm doing is taking an integral of this new expression, x plus 2 plus 2 over x plus 1 dx. And then, of course, it's time to actually take the antiderivative, right? That was my whole point, was to be able to take an antiderivative. So my antiderivative, let's see, my antiderivative of x would be 1/2 x squared. Antiderivative of 2 is 2x. Now, I want to talk about this guy for a second, this 2 over x plus 1. I'm actually going to pull off to the side here and work through that part of the problem. I'm hoping you don't actually have to write this out every time. I'm hoping that once you see the end result of what I'm about to show you, you will develop a pattern and then be able to just use that every time you do one of these. I'm sorry, the camera is very blurry today. See if that helps at all. So again, I'm going to just kind of look at this. What if I'm asked to do the integral of 2 over x plus 1? Technically, this is a U substitution situation. This is an x plus 1 inside like a fraction function. Okay, so I'm going to say, well, let's let u equal x plus 1. So then du is equal to, well, my derivative is just 1. dx, and that's really boring. This just means du is equivalent to dx, right? So when I rewrite my integral, I'm going to write it as the integral of, um, I'm going to pull this 2 off of here and make this a 1 over, and in place of x plus 1, I'm putting a u. So I just took the 2 off the top, put it in front. I actually could have put it in front of the integral symbol. Maybe I'll do that. That might look a little better. So I'm pulling that 2 off as a constant multiple. And I'm going to say this is 2 times the integral of 1 over u. And then dx is just equal to du. And then when I actually try to take the antiderivative of this thing you should recognize as natural log of x, or well, natural log of u. So this would be 2 times natural log of u. And then, of course, our natural log of u becomes natural log of x plus 1. So the point of all of that, sorry, I can squeeze that in there at the end. The point of all of that is when you have one of these fractions, and this is going to happen a lot with these division problems because it'll happen anytime you have a remainder. If it's just an x on the bottom, even if there's stuff added and subtracted with it, that's still just a natural log as far as an antiderivative goes. And any number that's hanging out up here on the top just becomes a constant multiple. So as far as finishing up my antiderivative here, antiderivative of that 2 over x plus 1 would be 2 natural log of x plus 1. And then, of course, this is an antiderivative with no endpoints, so I'm just going to say plus c. So this thing here, this is my final answer. Okay. So again, I'm not expecting this piece here in orange. I'm not expecting you to write that out every time. I just kind of wanted to justify to you where this piece was coming from. Okay, so now let's take a look at that next one. I could approach the next one the exact same way. I could do long division if I wanted to. I do also want to remind you about something called synthetic division. Now, synthetic division is quicker, but it's got some more limitations. It really only works if this factor down here is just a plain old x plus or minus something, an x minus 5 or an x plus 3 or an x plus 2 or something like that. If it's something other than that, your synthetic division is not going to work, okay? Because the synthetic division is based on the root that's associated with this factor. So if x plus 2 is a factor of whatever polynomial I'm dividing, the root associated with that would be negative 2. Okay, so that's the opposite of what I'm seeing there. And then I'm going to line up the coefficients from my original polynomial. So in front of the x cubed is a 1, and then a 3, and then a negative 5, and then a negative 10. Okay. I'm going to skip a line, draw a horizontal line. And again, this is something that you did see last year. And this is one of those things that I feel like sometimes it's easy to forget it, but it comes back really quickly once you see it again. The first number is always just going to drop straight down. And now what I'm doing is I'm multiplying here. So negative 2 times 1 is negative 2. And that number is going to go in this next blank here. So that's a negative 2. And then I'm adding 3 plus negative 2 is 1. Negative 2 times 1 is another negative 2. And when I add together, this is now negative 7. And then negative 2 times negative 7 is positive 14. And when I add together, that makes a positive 4. And that 4, that number on the end, that's always my remainder. Okay, so this is my remainder right here. And the reason these numbers are important is these are now the coefficients of the answer I would get if I did long division. Okay, so this started as an x cubed and I'm dividing by an x, which means this is really an x squared. So this is now 1x squared plus 1x minus 7. And then the remainder becomes a 4 over that x plus 2 that we were dividing by. And again, I only did that so I could rewrite my integral here. So now my integral is going to say, I'm still using 1 and 5 as my endpoints here. I don't have to do any crazy like conversions because I didn't actually change the x here. We're still talking in terms of x. I just algebraically moved that expression around. So now this is x squared plus x minus 7 plus 4 over x plus 2 dx. Okay. And now I have to take the antiderivative because that was the point, right? I might jump down here just a little bit for my antiderivative. So my antiderivative of x squared, I'm going to add 1 and then divide. So 1/3 x cubed. Same thing with the x. So that's now 1/2 x squared minus 7x. And then this, I'm using kind of the same idea I did up here. This antiderivative would be 4 natural log of x plus 2. And this time I'm not putting a plus c on there because I'm doing this from the endpoints from 1 to 5. So now I'm going to say, let's evaluate this from 1 to 5. In an ideal world, I would keep working over here to the right, but I'm going to have to jump down below here. And I'm going to wuss out of this one pretty early, but I do want to see, or I want you to see how I would write this out. And actually, I might even go lower so I have more space. The big thing to remember when you're doing these definite integrals is you're going to plug the top number in first, and you want to evaluate all of this together with that top number. And then you're going to plug the bottom number in, and you want to evaluate all of this together with that bottom number. And then the very, very last thing you're going to do is subtract them. And one of the mistakes I see quite a bit is people trying to just write down everything at once and then throw the subtraction sign in there. And if you miss those parentheses, that can really mess you up. So let me show you what I'm talking about. I'm going to do everything with the 5 first. Open a big set of parentheses. So 1/3 times 5 cubed plus 1/2 times 5 squared minus 7 times 5 plus 4 natural log. And I'm putting a 5 right here, so that's really going to become a 7. 5 plus 2 is 7. Close my parentheses. Minus, and let's open another parenthesis here. And now let's do the same thing with the 1. So 1/3 times 1 cubed plus 1/2 times 1 squared minus, whoops, I don't know why I put that other parenthesis there. Wasn't ready for that yet. Minus 7 times 1 plus 4 times natural log, and 1 plus 2 is 3. Okay, on a free response, you could get away with leaving this right here. On a multiple choice, you may have to simplify this, and I haven't actually worked through it yet. I don't think this is out of the question for you to have to simplify by hand. Okay, so I'm going to take the time to do that, but honestly, this is the calculus part up here. This is the algebra 2 part, and this is all just number crunching. This is older than algebra 2 even. So just so you kind of keep your priorities in order here. This is going to be 125 over 3. This is going to be 25 over 2. This is going to be 35. And then 4 natural log 7. The natural log 7, I'm honestly not going to do anything with. There are some things that I could do to combine it with this other natural log over here. We'll talk about that in a second. But I don't expect you to know natural log of 7. When I say simplify, you can leave it alone. Okay? Minus, now over here, I'm going to have 1/3 times 1 cubed, so that's just 1/3. Okay? 1/2 times 1 squared, that's 1/2. Minus 7, and then plus 4 natural log 3. Okay, and this is kind of what I mean. I guess this one's not going to help me quite so much, but if you keep things in terms of these fractions, watch like some of what's going to happen. So 125 over 3 minus 1 over 3. So I'm putting these two things together right now. And that's going to give me 124 over 3. I was actually sort of hoping that was something that would simplify a little bit more. I don't think it does because 124 doesn't divide evenly by 3. But this next one's a little more magical. So 25 over 2 plus 1 over 2. Well, that's 26 over 2. Oh, I'm sorry, not plus. It's minus. I forgot about this minus here. So 25 minus 1 over 2 is 24 over 2. Well, 24 over 2 is just 12. Okay? So all hope is not lost when you see those big scary fractions. Here I have a negative 35 minus negative 7. Okay, if it's minus negative 7, it's really a plus. So negative 35 plus 7 is negative 28. And then let's throw our natural logs in here, and I'll show you what we're going to do with those in a minute. They both have 4's in front of them. So I'm going to do this. I'm going to say it's 4 times natural log 7 minus natural log 3. Okay, because I could distribute that 4 back in there, and I would get a 4 in front of both of them. All right, let's clean this up a little bit more. I don't love this 124 over 3. I might wimp out a little bit here and say, okay, if this was 120, that would be 40, right? Because 120 over 3 is 40. So 123 would be 41. So this is really 41 and 1/3. I really hate writing fractions like that, but this is way easier on me mental math wise. 12 minus 28 is going to be negative 16. Okay. Just double check my math there. Yeah. And then plus 4 natural log 7 minus natural log 3. Okay. And then let's just do 41 minus 16. So that's 31, 30, 25, I believe. So this is now 25 and 1/3 plus 4. And then watch what I'm going to do here. This is really the part I was trying to get to for you. I want to remind you about something about logarithms that you should remember from last year. When you're subtracting logarithms, um, these two numbers can combine. So we can make this just a single log. We can just make this natural log of one thing. Okay. And that one thing depends on how you're connecting these. Well, if this is subtraction, I'm going to combine those numbers over here with division. So this would be 7 over 3. And I think the way you might actually see this on a multiple choice is, again, instead of this gross 25 and 1/3, although that was way easier to do mental math with here, I'd probably see it as improper fraction. So 25 times 3 is 75 plus 1 is 76. So I would probably see this as 76 over 3 plus, and then the natural logs would be combined this way. And that would be considered, simplified as far as I could possibly go. Okay. That's kind of gross, but it works. Hopefully you followed that. And then, like I said, I'm going to pick up another video to cover kind of the next set of examples.